Hello and welcome back to section 2.4 chain rule. And so now we are talking about differentiating something with the chain rule and having one of the other rules like product rule or something like that that we have to deal with. So that's what I noticed with this function here, that I start out there's an x squared times a chain rule, and so this thing is my chain rule when I have my square root in this function inside. So basically what's going to happen when I have to differentiate this, I have to remember that with my product rule, and I'll list out the product rule again, it's f prime of x, g of x, plus f of x times g of x times g prime of x. And so this becomes my f of x up here, the x squared, and then the square root function becomes the g of x. And so when I differentiate the g of x at the end down here, I'm going to have to go through and do a chain rule to do it. So that's kind of the key to this one. So if I ask you to find f prime of x of this function, it says differentiate the first, so that becomes 2x using just the power rule. Leave my square root alone, and I'm going to write it with an exponent, with a fractional exponent, just to make my life a little bit easier. And then I'm going to add on f of x, which is x squared, and now here's where the chain rule comes in. And I'm not going to go through the whole u substitution part, because I mean we've done it a couple times at this point. And also, I just want to make sure that you are this is the way you're going to end up doing it more often than not. So I differentiate the outside, which means the g of x is really 1 minus x squared to the 1/2. So we differentiate the outside, so we just use our power rule, 1/2, and we reduce the power by 1. So I get this 1/2 times the original function, 1 minus x squared, to the negative 1/2 power, just this part to the negative 1/2 power, and then I differentiate the inside, which turns into negative 2x. And so that is what I get when I do my chain rule, because I did differentiate the outside and then differentiate the inside. So now I get to simplify this thing, and because of this negative exponent, this is going to end up being a fraction. And so continuing on with my simplification, I'm going to have 2x times 1 minus x squared to the 1/2 power, plus, now I have 1/2 times my negative 2x, so when I combine those guys together I get a negative x, and then I multiply it by this, so really this becomes a minus x cubed. So minus x cubed, and then all of this goes over 1 minus x squared to the 1/2 power. And so this doesn't help me very much at this point, because I still cannot find where there might be vertical asymptotes or horizontal tangents or anything like that. So I need to get a common denominator. And so I have to multiply this side over here by my denominator of 1 minus x squared to the 1/2, top and bottom. And remember, by doing this, this is just multiplying by 1, so it doesn't change the problem, and it just is going to change the look of it. And so what I end up getting for this is the denominator of this function ends up being exactly what we see, 1 minus x squared to the 1/2 power, and then the top, when I multiply this together, well, what happens is I can take the 1/2 times the 1/2, and those become a full thing, because remember the same bases add together. So really we end up with 2x times 1 minus x squared, which makes things much better for us, and then we've got minus x cubed. And so when we continue on with this, just a little bit of simplification, distribute and simplify, we can end up with 2x minus, I'm just going to distribute, there's my 2x, and then this guy gives me negative 2x cubed minus x cubed all over 1 minus x squared to the 1/2. And so my final answer, my f prime of x, will simplify down to minus 3x cubed plus 2x all over 1 minus x squared to the 1/2 power. And then having it written this way gives me a lot more power to find horizontal tangents or vertical asymptotes. So continue on with the next example, we end up with this one is going to be a quotient rule that we have to do. So we have to remember our quotient rule, which is f prime of x, g of x, minus f of x times g prime of x all over g of x squared. And so there's my quotient rule, and so the reason I know it's a quotient rule is because I've got an x on top and x is on the bottom. But when I have to differentiate the g prime of x again, then this is where I end up having to do a chain rule, because this is a cube root function which is outside of my x squared plus 4. And so that's really what we're dealing with. So right here at the end when I do g prime of x, that's where I'm going to have to do my chain rule. So if I go ahead and differentiate this, I get f prime of x, and so differentiating x, my f of x gives me 1, that's not so bad, and then it's times g of x, which happens to be, I'm going to write it as x squared plus 4 to the 1/3 power. And I like using fractional exponents instead of the roots, it just makes things easier. And then I get to subtract away the f of x, and now here's where the trick comes. I have to do my chain rule. So if I differentiate the outside, and I'm going to look at this guy right here because it's written out the way I want it, I'm going to differentiate the outside, which means I multiply by 1/3, and then I just leave the inside function alone and reduce the power by 1, which gives me negative 2/3. And then I have to differentiate the inside, which is 2x. And so then there's that, and then the whole bottom part is just what we see. And I'm going to write it like this, x squared plus 4. Now it would be 1/3 if I left it as a single one, but since I'm squaring it, I'm going to use 2/3 as my denominator. And so now the trick to this one is going to be the simplification, and basically what you're going to see is that this thing's going to break into two different fractions as I do this. And so I'm going to do f prime of x will give me over here I have x squared plus 4 to the 1/3 power all over, well, that just got really sloppy. Let's try that again. X squared plus 4 to the 1/3 power is going to be over my x squared plus 4 to the 2/3 power. And then over here, when I get stuff together, I'm going to have, it looks like a negative x squared, a negative 2x squared, all over 3 times x squared plus 4 to the 4/3. And what I did is, I remember this guy's on the wrong side, and since this thing is the same base as that, I end up taking the 2/3 and adding them together and getting 4/3. And the 3 that came on the bottom was from right there, the 1/3. So that's that and the 2. So hopefully you can see that. So now I got to get a common denominator, which means this guy, top and bottom, needs to be multiplied by 2/3 to get this 1 to 4/3, and by 3. So I have to multiply by 3 times x squared plus 4 to the 2/3 top and bottom. 3 times x squared plus 4 to the 2/3 top and bottom. So now what that will get me for my derivative is, well, I'm going to have 3 times this thing, but since 2/3 and 1/3, same base, add the exponents together to 1, it really works out kind of nice in this case. I just end up with 3 times x squared plus 4 to the 1 power minus 2x squared all over 3 times x squared plus 4 to the 4/3 power. And then I can simplify the top a little bit more. If I distribute my 3 to both of these guys, I get 3x squared minus x squared, 2x squared, which should give me an x squared, and then plus 12 all over my denominator of 3 times x squared plus 4 to the 4/3 power. And that's the derivative I'm looking for, and that's probably the form we want it in, just for the fact that we can find, like I said, vertical asymptotes and also horizontal tangents, which are things that are very important. So in the next example, this time we have a whole function that is being squared, and this time it becomes a little bit more of a problem that in order to differentiate this, I'm going to have to use the chain rule. And so this is it's the chain rule on the outside, but then when I differentiate the inside, I've got to use a quotient rule. So that's kind of the way this is going to start. So if I'm going to differentiate this, I'm going to say dy over dx. And now when I differentiate the outside, that means this is the outside function, the 2. So it's 2 times the inside function, which is 3x minus 1 over x squared plus 3, reduced by a power of 1, so there it is. And then I get to multiply by the derivative of this thing, which becomes a quotient rule. And so in order to do the quotient rule, it's the derivative of the top, which will give me 3 times the bottom, x squared plus 3, minus leaving the top alone, 3x minus 1, and the derivative of the bottom, which is 2x, and then all of this is over the bottom squared, x squared plus 3 all squared. And so that's basically what I end up with this problem, and then it's a lot of simplification. So since this is to a power of 1, I can just kind of multiply. I could distribute, or I'm going to actually simplify the top over there before I really get to work. Dy dx, and I'm going to distribute the 2, because remember 2 is 2 over 1. So I really have 6x minus 2, and then the bottom of this is x squared plus 3, and that's going to be multiplied by this whole thing. And so I'm going to distribute my 3, which gives me 3x squared plus 9, and then when I multiply these guys together, I get a negative 6x squared and a positive 2x. And then the bottom is still what it was. It's the x squared plus 3 squared. So combining like terms on top, it looks like I have I'm just going to combine them right now, just up top here. That's a negative 3x squared positive plus 2x plus 9. So that's really what this top part is. And the reason I did that is just to save me some time here, because now I got to multiply these together. And actually, I'm not even going to do that. Your final solution for this, at least as far as our concern is multiply the bottoms together, which is adding the exponents. So we end up with x squared plus 3 cubed. And on the top then, I wouldn't even bother multiplying these together unless the answer on either the AP test or your test require it. But this is as far as I would go, because it's enough with their zero product property from Algebra 2 and Algebra 1 that we can use that to help us find the horizontal tangents on the top. So that would be enough for us. So that would be enough simplification. We don't need to go any further than that. And so I'm going to continue on with part 3 of this in another video. So please tune in to part 3.